Hi, my name is Amber Naranjo, and today I will be presenting my term project for CAP 6673, Data Mining and Machine Learning. For this project, I was given the following baseline paper. Using correlation-based feature selection for a diverse collection of bioinformatics datasets. Contributors of this paper are Randall Wald, our professor, Dr. K, and Amri Napolitano. The topic of correlation-based feature selection is quite broad, therefore this presentation will focus specifically on my assigned paper. The contents for this presentation are as follows: introduction, critiques, issues, techniques, datasets, results, summary, conclusion, and references. Introduction. What is bioinformatics? What is correlation-based feature selection? What is bioinformatics? Bioinformatics is the science of collecting and analyzing biological data such as genetic codes. In particular, this paper focuses on gene microarrays, also known as gene chips, which is a technology in the domain of bioinformatics used to detect the expression of thousands of genes at the same time. What is correlation-based feature selection? Correlation-based feature selection, also known as CFS, is a measure used to evaluate subsets of features based on how correlated its features are with the classification. A feature subset is considered good if it contains features which are highly correlated with the class but not correlated to each other. This correlation metric is based on the Pearson correlation coefficient. In general, a correlation between 0.5 and 1 is considered strong, while correlation less than 0.5 is considered weak. The formula for the Pearson correlation is defined on the right. Critiques. Critiques of the current approaches involving CFS. Critiques involving correlation-based feature selection. Correlation-based feature selection is considered computationally expensive. Few works have employed filter-based subset techniques such as CFS, which detects non-redundant and small feature subsets. Of those few works which have successfully utilized CFS in this particular area of interest, that is, bioinformatics, only a small collection of datasets have been used. Moreover, these limited works which do apply CFS to bioinformatics datasets fail to consider important dataset properties such as class imbalance and difficulty learning. Issues. What are the issues identified? What are the issues? Gene microarrays contain tens of hundreds of genes, and this high dimensionality makes feature selection difficult. The computational cost of correlation-based feature selection and other such filter-based subset evaluation techniques makes them difficult to implement on very large datasets. The general challenge of feature selection is reducing the number of features in a dataset. Filter-based feature ranking is more computationally efficient than filter-based subset evaluation and wrapper-based subset evaluation, but has the issue of being unable to recognize redundant features and only being capable of discarding irrelevant features. Filter-based subset evaluation and wrapper-based subset evaluation have the opposite issue of filter-based feature ranking. Although they are able to detect both irrelevant and redundant features, they are computationally expensive, with wrapper-based subset evaluation being the most time-intensive. Issues continued. Issues which can affect a wide range of gene microarray datasets are class imbalance and difficulty of learning. Class imbalance happens when each class fails to make up an equal portion of the dataset. And difficulty of learning happens when datasets are noisy or have a very weak class boundary. Techniques. What are the techniques used to combat the issues? What are the techniques used? Correlation-based feature selection. As described in the introduction, correlation-based feature selection is an ideal method for feature selection. Although this technique has issues performing successfully on high-dimensional datasets, such as the gene microarray datasets in question, this experiment proceeds by employing correlation-based feature selection on 9 different microarray datasets. Each of the 9 datasets exhibit a wide range of characteristics regarding the issues mentioned previously of class imbalance and learning difficulty. Learners. In conjunction with correlation-based feature selection, 5 different classification learners are used. 5 nearest neighbor, also known as 5NN, logistic regression, also known as LR, multi-layer perceptron, also known as MLP, naive Bayes, also known as NB, and support vector machines, also known as SVM. Techniques continued. Performance measurement and cross-validation. The classification models for this study were built and tested via 5-fold cross-validation. For the purpose of giving a broader perspective, 5 different performance metrics were also used. Area under the receiver operating characteristic curve, also known as AUC. Area under the precision recall curve, also known as PRC. Best arithmetic mean, also known as A-mean. Best geometric mean, also known as G-mean. And default accuracy, also known as ACC. Datasets. A description. Description of the datasets. There were 9 different datasets used in this particular study. All 9 of the datasets used are gene microarray datasets. The features are representative of various genes' expression levels measured by how strongly the varying gene probes react to the mRNA produced from a tissue sample. The class values are all binary, and they are based on if a patient has cancer, what type of cancer they have, or if they responded well to a certain cancer treatment. The table on the left shows details of the datasets, including dataset difficulty, dataset name, number of minority instances, total number of instances, percent of minority instances, number of attributes, and average AUC. Those datasets shown in red represent balanced datasets, and those datasets shown in green represent imbalanced datasets. Description of the datasets continued. The average AUC depicts the classification performance on these datasets when models are built without feature selection. AUC performance defines difficulty of learning as follows. Easy learning, average AUC greater than or equal to 0.8. Moderate learning, average AUC less than 0.8 and greater than or equal to 0.7. And hard learning, average AUC less than 0.7. Results. Results for building classification models using CFS for feature selection. Results using CFS. Upon the datasets having CFS applied to reduce their features, the results were averaged across all 9 datasets and can be seen in the table on the left. The 5 nearest neighbor learner appeared to be the best learner for 4 out of the 5 performance metrics. The logistic regression learner was the worst learner across all 5 performance metrics. And the support vector machines learner was the best learner for the area under the receiver operating characteristic curve performance metric. As you can see on the table to the left, those values shown in red represent the best learner for each performance metric, while those values shown in green represent the worst learner for each performance metric. Results continued. The table on the left shows the results broken down according to their difficulty levels. For the easy datasets, MLP was the best learner in terms of PRC, and 5NN was the best learner for all other performance metrics. On the other hand, NB was the worst learner in terms of PRC, and LR was the worst learner for all other performance metrics. For the moderate datasets, SVM was the best learner in terms of AUC, and 5NN was the best learner for all other performance metrics. On the other hand, LR was the worst learner across all performance metrics. For the hard datasets, the best learners had more variation depending on the performance metric. 5NN was the best in terms of ACC, MLP was the best in terms of PRC, SVM was the best in terms of AUC, and NB was the best in terms of A-mean and G-mean. As with the moderate datasets, LR was again the worst learner across all performance metrics. Overall, LR tended to be the worst learner across all difficulty levels. Again, we see on the table shown to the left that the values shown in red represent the best learner for each performance metric, while the values shown in green represent the worst learner for each performance metric. Results continued. The table on the left shows the results broken down according to their balance levels. For the balanced datasets, SVM was the best learner in terms of ACC, and 5N was the best learner for all other performance metrics. On the other hand, NB was the worst learner in terms of ACC, and LR was the worst learner for all other performance metrics. For the slightly balanced datasets, 5NN was the best learner in terms of PRC and ACC, and SVM was the best learner in terms of AUC, A-mean, and G-mean. On the other hand, LR was the worst learner across all performance metrics. For the imbalanced datasets, MLP was the best learner in terms of AUC, PRC, and ACC, and NB was the best learner in terms of A-mean and G-mean. As with the slightly imbalanced datasets, LR was again the worst learner across all performance metrics. Overall, LR tended to be the worst learner across all difficulty levels. Again, we can see that on the table shown to the left, that the same key is used. The values shown in red represent the best learner for each performance metric, while the values shown in green represent the worst learner for each performance metric. Summary. Summary of the study of using CFS for a diverse collection of bioinformatics datasets. Summary on correlation-based feature selection study. Filter-based subset selection techniques, like CFS, can detect small and non-redundant feature subsets. This is very useful when it comes to bioinformatics datasets, and in particular, gene microarray datasets, which typically have such a large number of features. This study aimed to address the issue of the high dimensionality found in such datasets. CFS was conducted over 9 different gene microarray datasets. Each dataset contained 3 different levels of class imbalance and 3 different levels of difficulty of learning. 5 different learners were used to build the classification models, and 5 different performance metrics were used to evaluate them. The effectiveness of the models built using CFS were then showcased appropriately. Conclusion. Conclusion on the study of using CFS for a diverse collection of bioinformatics datasets. Conclusion on correlation-based feature selection study. Some datasets were more definitive than others. The easy level datasets, moderate level datasets, and balanced level datasets unequivocally showed 5NN to be the best learner. The other dataset categories were less assertive in their findings. Neither the hard level datasets, slightly imbalanced level datasets, nor the imbalanced level datasets had a conclusively best learner. However, SVM generally did well in terms of AUC, NB was best in terms of A mean and G mean, and at times, MLP performed well. Generally, LR was the worst learner across all dataset categories. Overall, the PRC performance metric resulted in atypical behavior with regard to the other 4 performance metrics used. The resulting PRC values dropped off between the easy level datasets and the moderate level datasets, as well as between the slightly imbalanced datasets and the imbalanced datasets. This drop was considerably greater for PRC than any other performance metrics. References. References cited during presentation. The references cited during the presentation can be seen below. In particular, these references can be traced back to the data sets used for this experiment.